Today we will start with gases unit, and on this unit we will have 3 lessons. The first lesson will be regarding the properties of gases, combined gases, Charles Boyle's and Gay-Lussac laws, and the second one will be in the relation to kinetic molecular theory, ideal gases, Avogadro's law, and molar volume. And the last one will be a review of gases. So the outline of the first lesson, which we will deal with today, is the properties of gases, STP and SATP, absolute zeros, and knowing the relationship between pressure, temperature, and volume in all of the gases law, like combined gases, Charles Boyle's and Gay-Lussac gases, and to be able to determine which law gases are you using. So let's start with the properties of gases. What are we going to explore on this unit is the relationship between pressure, and the pressure is identified with capital letter P, and the definition of the pressure is the force per unit area. So there are plenty of units that the pressure is measured, but what we will be focused mostly on Chem 20, or for this course will be kPa, atmosphere, and mmHg. Another quantity that we will work and discuss on this in terms of the properties of gases is a volume. And the volume, we have to keep in mind that gases fills the volume of the containers that they are in. So they do not have a specific or a defined volume, but they take the volume of the container that they are in. Volume is identified by letter V, capital V, and it is measured in liters. The third quantity that we will talk and discuss on this in terms of the properties of gases is temperature, and it is identified with capital letter T. So often for temperature, we will see a capital letter T, which will mean that we are dealing with Kelvin, and a lowercase of t, which will mean that we are dealing with Celsius scale or degrees Celsius. On the formulas that we will implement and we will apply, it is the units that we will use is Kelvin. It's the Kelvin scale. The last property or a variable that we will discuss is the amount. When we say amount, is the amount of gas, which can be given in grams or kilograms or on that realm for weight units, but actually is identified with a lowercase n, because we should be able to convert, even if it is grams, into number of moles using the conversion that we have discussed in Review of Science 10. So this n is actually the number of moles that this amount of gas is having. Now, the properties of gas that we have to keep in mind is that occupies the volume of the container that it is. We mentioned it, the volume of the container that it is. So it doesn't have their own shape. They are highly compressible. So we can apply compressible. We can apply a high pressure. And what we will see in this unit, even through the different laws, is that volume, pressure, and the temperature are interrelated between each other, which means that when we change the volume, if we keep the temperature constant or not, then the pressure will change and vice versa. Okay, so now when we talk about STP and SATP, this is not STP, but it is SATP conditions. What we have to keep in mind is that STP stands for standard pressure, temperature and pressure, temperature and pressure. Temperature and pressure. Okay, so when we say that a certain gas is at STP conditions, what do we mean is that it has a temperature of 273.15 Kelvin or 0 degrees Celsius and a pressure of 1 atmosphere or 101.325 kilopascal. Also under these conditions, 1 mole of gas, any gas, occupies 22.4 liters per mole, which is known as the molar volume. So now in your data booklet, what I want you to write is STP conditions are temperature is 273.15 Kelvin or 0 degrees Celsius. Pressure is 1 atmosphere or 101.325 kilopascal, so that you have those notes and you refer to them as often. Molar volume is 22.4 liters per mole. Okay, and then SATP condition stands for standard ambient temperature and pressure. Okay, so when we are talking about those pressures in terms of the numbers, what do we have is a 298.15 Kelvin or 25 degrees Celsius and a pressure of 100 kilopascal. And under the SATP conditions, so the molar volume is 24.8 liters per mole. Again, what do you have to do is write in your data booklet, SATP conditions are temperature 298.15 Kelvin or 25 degrees Celsius. Pressure is 100 kilopascal and molar volume. We will use all those numbers, so please have those ready. Now, when we are converting, what we have to keep in mind is that 101.35 kilopascal is 101 atmosphere or 760 mmHg. And then in terms of the temperature, when we are moving, if we know Celsius and we want to figure out what is it in Kelvin, then we add 273.15. And if we know Kelvin and we want to convert it into degrees Celsius, then we subtract from it the value of 273. Absolute zero means 0 Kelvin, 0 Kelvin degree. Oh, yeah, it's our Kelvin scale, which in theory means that this is not, you cannot reach this temperature, but in theory, what it means that the nothing is moving. Okay, so nothing is moving. Let's see some conversion examples. So now we have 2.00 atmosphere to convert it into kilopascal. So what we have is 101.325 kilopascal is equal to 1 atmosphere, or if we have 1 atmosphere, then we have 101.325 kilopascal. So now we start with what is given, 2.0 atmosphere, and then we use the unit conversion, which in this case we will use the first ratio out of those two ratios, because we want to cancel the atmosphere that is at the top. So then we need an atmosphere at the bottom, and this will be 101.325 kilopascal. So the units that we are ending up having will be in kilopascal. Keeping in mind the significant digit, we can say that the pressure of 2.0 atmosphere is 203 kilopascal. Now, next one is we are converting 250.0 in kilopascal into mmg. So now what we have is 760 mmHg is equal to 101.325 kilopascal, or 101.325 kilopascal is equal to 760 mmHg. So now we start with what is given, 250 kilopascal times, using the unit conversion, we will choose to use a ratio 1 because we want to cancel the kilopascal units that are at the numerator, so we need them into denominator. And 760 mmHg. So kilopascal and kilopascal is cancelled out, and then the calculator will tell us that it is 1875 mmHg, and that we are writing the final answer with 4 significant digits, since whatever the problem is starting with has 4 significant digits. Let's take a look at the other one. So now we have a tire that has a pressure of 873 mmHg, but the pressure gauge measures in atmosphere. What will the reading be? So on this case, what we have to use is the fact that 1 atmosphere is 760 mmHg, or 760 mmHg is 1 atmosphere. So now we start with what is given, 873 mmHg, and we choose and we discuss which ratio are we using. Are we using ratio 1 or ratio 2? We will use a ratio 1 because we need to cancel the unit, so 760 mmHg. And so then we cancel those two, and then what the units that we will have will be in in atmosphere, and using the calculator we will have, it is 1.15 atmosphere. And again, what we are doing here, we are saving or we are honoring the significant digits rule. Now, when we are converting into Kelvin, or Kelvin to Celsius, or Celsius to Kelvin, what we are keeping in mind is Kelvin is degrees Celsius plus 273.15, and degrees Celsius is equal to Kelvin minus 273.15. So now we have Kelvin, and we will use, or will convert them into degrees Celsius. So degrees Celsius will be equals to 294.25 minus 273.15, and this will be 21.1 degrees Celsius. And when we are converting Celsius into Kelvin, then what we will do is we'll use this equation here. Kelvin will be 90 degrees Celsius plus 273.15, and this will be equal to 363.15 degrees Celsius. Okay, now to go from 222 Kelvin into 322 into 302 Kelvin, there is a decrease of 20 on Kelvin scale. And to go from 67 to 47 will be again a degree or decrease of 20 on Celsius scale. Now, what do you have to keep in mind is that if the temperature, if temperature is increased at an X amount by X amount, whatever is the amount, it doesn't matter what, in which scale is it increased. If it is increased by X amount at Celsius, will be the same increase, the same amount increase in Kelvin scale. So if the amount, so if we're saying increase of 15 in Celsius will be reflected increase of 15 on Kelvin. However, if the temperature is increased by a factor of, meaning that is multiplied, is changed, I will say, is changed by a factor of n, this is not the same change happening on the other scale. So let's say this is in Celsius. Is not, and this is important, is not reflected the same factor on Kelvin. So if the temperature is increased by a factor of 2, it's not the same effect on the Kelvin scale. It's not increased by a factor of 2 even on Kelvin scale, and or vice versa. Okay, so if you are multiplying, let's say, Kelvin by a factor of 2 or 1/2 or 1/3, that doesn't mean that the same increase will happen at the Celsius scale. The same factor increase or decrease will happen at Celsius scale. So, but if you are increasing the amount or decreasing the amount, so if you are increasing it 20 degrees on Celsius, 20 degrees will be on Celsius as well. So now when we talk about combined gas flow, what do we have to keep in mind? That this gas law explores the relationship between pressure, volume, and temperature when the number of moles is kept constant. So the amount of gases. Mathematically, this relationship can be expressed as the ratio of the product pressure and the volume with temperature is constant. So pressure and a volume over temperature is constant when the number of moles is kept constant. In other words, that means that the product of pressure and volume over temperature on the initial is the same as the product of pressure and volume on temperature of the final or the second situation. So P1 V1 over T1 is equal to P2 V2 over T2, where 1 is the initial and 2 is the final, let's say. So this means, in other words, you can, if you cross multiply them, then you will have P1 V1 T2 is equal to P2 V2 T1. You can see this law in those two forms, and this is known as the combined law. Now let's see and do some manipulations in regards to finding the volume or finding the pressure or finding the temperature. The easiest one is to cross multiply them. Okay, so when we have P1 V1 over T1 equals to P2 V2 over T2, and we are solving for, let's say, T2, then what we do is we just T2 switch places. We cross multiply and switch places. So P2 V2 times T1 is equal to P1 V1. Even from this relationship here, you can get this. Or if we have P1 V1 T1 equals to P2 V2 T2, and we are solving for V2, then what we do in this case is that we go P1 V1 T2 equals to P2 V2 T1, and then divide both sides by P2 T1 so that those are canceled out, P2 T1, and then V2 will be P1 V1 T2 over P2 T1, and this will be the relationship that we will use. Or if we have to solve for, so we have P1 V1 T2 equals to P2 V2 T1, and we are solving for P2 in this case. Then what we do is we divide both sides by V2 T1. So we'll have P2 is equal to P1 V1 T2 over P2 T1. And this will be the relationship that we will use on this case. Let's see an example here. So we have an example of an ethane gas that has a volume of 35. So volume is equal 35 liters, and temperature is 25 degrees Celsius, which in Kelvin will be 25 plus 273.15. And this is V1, okay? And then P1, this will be T1 as well. P1 will be equals to 100 kilopascal. And then for the second situation, or as the second situation, we will have P2 at 85 kilopascal, and V2 is unknown, and T2 will be 35 degrees Celsius, which converted into Kelvin will be 35 degrees Celsius plus 273.15. Okay, so now if we are doing those calculations, we will have 308.15 Kelvin, and for the temperature one, we will have 298.15 Kelvin. So now what we are looking for is V2, so you can go even P1 V1 T2 equals to P2 V2 T1. From here, we find that V2 is equal to P1 V1 T2 over P2 T1. Let's substitute what is given. So V2 will be P1 is 100 kilopascal. You will see that all the units will cancel out. Times V1 is 35 liters. Times T2 is 308.15 Kelvin over P2 is 85 kilopascal times 298.15 Kelvin. So now what we have, it's kilopascal and kilopascal is cancelled out, and Kelvin is cancelled out. So then the volume will be on liters, and it is 43 liters. If you don't go with the calculations, and you will find that it is 43 liters. Okay. Let's move to a second example here when we have a volume of 3 liters and is held as a temperature of 298 Kelvin at a pressure of 200 and a pressure of 230 kilopascal. And then what do we have is that what will the volume of the gas be if the pressure drops at, so pressure drops at 100 kilopascal. Okay, so now since the temperature on the second one, on the second situation is not mentioned, then the assumption that we do here is that the temperature is the same, T1 and T2 is the same as 298 Kelvin. So when it is not mentioned, then you state that the temperature is the same. So now what we have is P1 V1 T2 equals to P2 V2 T1. Since this is the same, we can simply cancel it out, and then we will have to figure out what is V2, because this is what they are asking for, what is the volume. V2 will be P1 V1 over P2. And if we substitute, what do we have is 230 kilopascal, and still the units will cancel out, times 3.0 liters over 200 and what? No, sorry, it's 100 kilopascal. So kilopascal and kilopascal is cancelled out, and then volume on the second case will be 6.90 liters. And this is taken into the consideration the fact that the number of sigdigs is 3. Okay, let's move to Another example here where we have STP and SATP. So what is given here, the only thing that is given here is the volume. So let's sort out but we know that what are SATP and what are STP conditions. So again, this is why having that into your data booklet will help you. Okay, so in the first case, when it is at SATP conditions, P1 will be equal to 100 kilopascal. Volume 1 will be equals to 40, what is given in liters, and the temperature will be, temperature 1 will be 298.15 Kelvin. We know this from the fact that we are dealing with SATP conditions. And now, it is what is happening is undergoing into STP conditions, which means that P2 will be equals to 101.325 kPa, and volume 2 is unknown. This is what we will figure out. And then temperature 2 will be equals to 273.15 Kelvin. So now volume 2, let's go straight to the formula because we have done this so many times. V1 T1 P1 T2 over P2 T1 will be 100 kilopascal times 40 liters times 273.15 Kelvin over 101.325 kilopascal times 298.15 Kelvin. Simplifying or canceling out the units, we will have the units of liters ending up, and what the calculator is giving us will be 36.2 liters. The calculator itself gives you 36.17 liters, but considering the number of SIGDIGs, you write it as the final answer of 36.2 liters. Okay, let's move to next example. So at SATP conditions, a gas has a volume of 50.3. What is the volume if the pressure drops at 85 kilopascal and the temperature rises to 30.2? So now we are at SATP conditions, which means that pressure 1 is 100 kilopascal. Volume 1 is given at 50.3 liters, and the temperature 1 based on SATP conditions is 298.15 Kelvin. And then pressure 2 is 85 kilopascal. And temperature 2 is 30.2 degrees Celsius, which will be in Kelvin as 303.35 Kelvin. And what we are looking for is a volume 2, and I will write the formula P1 V1 T2 over P2 T1, and this will be 100 times, now not writing the units since we know that everything will cancel out, 303.35 over 85 times 298.15. And then the volume 2 will be 60.2 liters. And again, always keep in mind that the final answer should be at the correct number of SIGDIGs. Okay, so now let's see what is happening here. The next example is what factor will temperature change in Kelvin if pressure is doubled and volume is tripled? So if we have a pressure 1 P1 and a volume 1 V1, then T1 will be a certain value, T1. And this is the first situation. And for the second situation, we'll have P2, V2, T2. But now what do we have for P2 is that, oh, let's not do that this way. So now what the combined law of gases is saying is P1, V1, T2 equals to P2, V2, T1. Okay, so now what do we have? P1, V1, T2 is equal to P2. We said that is doubled, pressure is doubled, meaning that is 2 times whatever it was initially. So this is for representing the P2. And now what do we have for volume is tripled. So that means that volume 2 is becoming now 3 volume 1 times T1, that was whatever value it was originally. So now what do we have here is that P1 V1 T2 equal to 2 times 3 is equal to 6 P1 V1 T1. Okay, P1 V1 is the same in both sides and multiplied, so we can cancel it out. So that means that T2 is equal to 6 times T1. So you can say that the temperature in Kelvin is increased by a factor of 6 in comparison to the initial temperature. Keep reminding yourself that if this was asked, then second question was like, what is the temperature factor? What factor the temperature will change in Celsius? It's not 6. Definitely, it's not 6. It's something else. You have to go through the calculation. So because it is not the same factor that we implement.